going to talk about some possible atmospheric color changes that happens prior to large magnitude and also some local earthquakes. We have at the observatory in Sedona a camera, an all-night camera that takes pictures once every minute. Oh, that's better. Once every minute, all night long. And we have observed some chromatic shifts before large magnitude and local earthquakes. We've also observed what could be infrared flashes and some suggestion of ultraviolet flashes and some GPS disturbances. The photograph suggests that anomalies can be detected over great distances, very surprising. And we are questioning both ultraviolet and infrared transmission, how they might across great ranges. We're looking at possible mechanisms, which are very, very speculative at this time. We're looking at air refractive index, ionospheric changes, and total electron content. We'll end up looking at a possible, simple, inexpensive way to detect the timing but not the location of large earthquakes. It started a long time ago. Since the 1980s, I have been residing in the Bay Area and noticing that prior to the California earthquakes, which are almost constantly ongoing, that you would see atmospheric color changes. I don't know how well you can see them in the slide here, but the sky would take on kind of a reddish, ruddy hue before the earthquakes, and I have probably taken a couple hundred photographs of this phenomena. This is a normal sky color, and smog is usually white to yellow. So there is something peculiar about the color changes here. Fast forward into the future here. Other people have reported optical anomalies prior to earthquakes, but they haven't been well documented. So here are just a couple. This is before the Sichuan earthquake in China. You can see this as a video on YouTube. There was a fire rainbow that was taken by two separate individuals 30 minutes prior to the Sichuan earthquake. And here, Aquila, Italy, these photographs were taken about 10:30 at night, so this is not a sunset. You'll see the purple color and this sort of rose color, and you'll see a lot more of that in my slides, that the entire horizon lit up. Now, this is a reason you can't try this at home, or at least not very well, that humans are basically colorblind at night. And so our rods work, but our cones that perceive color can't work. This is a picture of a sky glow that was very, very bright that occurred in Sedona just prior 9 and 10 hours to two large magnitude earthquakes. And this photograph has been changed so that you can actually see what we saw with our eyes, which was basically a black and white sky glow. It looked like a big lens overhead. It looked like there was a full moon. It was as bright as a full moon looking through the clouds, except there was no full moon. It was very close to the new moon, and the new moon was just about setting in the opposite direction. This is what the camera sees. The camera can see far more colors at night than humans can with our eyes. Okay, basic primer on the colors that are normal and natural for the camera to see during quiet seismic periods. The color depends really on the moon. If the moon is up and there are a few clouds, you'll see this basically gray sky and gray to blue. And if the moon has set, you'll see a sort of a ruddy hue, and things are fairly dark. The sky is black. You can see stars quite vividly. The progression of the moon, you can see here is twilight up here, and you'll see the gray sky, and then as the moon sets, you'll see very consistent colors fading into this basically red. And that was during a seismically quiet period where there had been no magnitude 6 earthquakes for more than a week. During the full moon, you'll see a pale blue sky with the clouds. The clouds are basically white. This is what we see prior to large earthquakes or local earthquakes. This is normal, but we will see glowing storm clouds. We will see rose colors, purple colors, and aqua ultramarine colors. And these color shifts happen. They're very intense and they're very rapid. They take place often within less than a minute. This is an example of a chromatic shift. You can see a deep ultramarine, which is not a normal color, and then you'll see it going to a purple hue. I hope you can see it with this projector. And then here, it's fading back to the ultramarine very, very quickly. These are 1 minute apart. All of the photographs that I'm going to show you happen in the middle of the night. These are not dawn or sunset pictures. Prior to large magnitude earthquakes, we see about 7 to 8 days we begin to see these chromatic shifts, and they tend to maximize about 3 to 4 days in advance. And the day of the earthquake, oftentimes we will see the situation change back to normal, although sometimes we do continue to see shifts. We're going to look at 6 earthquakes, the 3 largest earthquakes that have happened during the time that these cameras have been in operation. We'll look at the largest and closest earthquake, which was Mexicali 7.2, and 2 really anomalous earthquakes that occurred just 12 miles from where we are in Sedona. And this is significant because earthquakes basically don't happen in Arizona, and there is no historical record of earthquakes happening in this exact area before. Okay, I'm going to cut to the chase here and show you very rapidly the chromatic shifts that precede earthquakes, and not dwell on them, but what I would like you to observe is the variability in the colors. And you've seen the controls, and look how the colors change starting 7 to 8 days, maximizing about 4 days prior to earthquakes. We'll go into the time machine now, and we will go and look step backwards from 8 days out to the time of the earthquakes. The first earthquake is an 8.1 at Samoa. This earthquake occurred about 4,500 miles away from the Sedona Observatory. Here you'll see the normal moon set colors, but then all of a sudden you'll see color shifts to gray and then back to the ruddy color, and so on and so forth. And you see this continues through day 7. And then at 4 days you'll see some new colors come in, this sort of an aqua color and maybe a little bit pink. And you can see the variety of colors that are occurring. Here's an example of a chromatic shift that has happened in just 1 minute from an ultramarine to back to a normal gray, so this is an enlargement. Also, quite significant, I was hiking just before the 2 days before this earthquake, and I could not receive satellites on my GPS receiver. Okay, a little bit more than a day, you see the colors change, but you will see these shifts continuing. There's a bright moon up now. And after the moon sets, you'll see the shifts between gray and rust color. At 10 hours away, you see continuous shifting. Okay. The next earthquake was magnitude 8.8 at Chile. And again, this was more than 4,500 miles away. And you'll see some new colors, which are kind of a rose color and then fading back to gray. This is with the moon is up, and then you'll see some clouds come in that start glowing yellow. A storm came in, and the clouds became very, very luminous, and you can see all of the variety of intensely glowing colors. At that point in time, the camera broke down. I had a second camera, fortunately, in operation, facing in a slightly different direction. And you can see that another camera, this is not a camera artifact, that this second camera also picked up all of the color shifts, even though it was in a different direction, different camera. 4 days, I saw a color that I had never seen before the Chile earthquake, which was this very intense pinky purple color. And this lasted for a long time. Usually we just see colors lasting for a few minutes. And here's an example of the pinky purple color, and you notice that the rocks here in the foreground seem almost iridescent. And then 2 hours later, you can see that things have changed back to normal. -2 days, the moon is up and bright. There's some clouds, but you can see that the colors continue to shift. Also 2 days, there's a rose color that begins. 1 day, you can see the color continue to shift. And then things kind of stabilize out, even though this color is not really a normal color. The normal color is gray, but the fluctuations have basically stopped. And at the exact time of the earthquake, it's a full moon, it's overcast, and there are no chromatic shifts occurring then. One difficulty is that we can't really see this with our eyes because our receptions, even in good lighting conditions, aren't very good in the ultraviolet and ultra-red, or infrared. But this color here had a kind of a reminiscent ring to it to me, and so did this, because I'd done some previous tests of the cameras, and I'd found that the cameras can see a little bit more beyond the optical spectrum. They see a little bit more into the ultraviolet and a little bit more into the infrared. So the test that I have done with some transmission filters, this is what the same scene looks like in the ultraviolet and in the infrared. And these seem to match somehow, at least in a suggestible sense, that perhaps we had some ultraviolet and infrared components to the lights that we were seeing. Here is an infrared flashlight, and again, by comparison. So being a nonprofit organization, in order to test the hypothesis, if there was infrared involved in some of these color shifts, we chose a very quick and dirty, cheap way of detecting infrared, which is a motion sensor floodlight. And what I did was to set the floodlight up in the same direction the camera was facing, and whenever it detected an infrared signal, it would illuminate the bushes in the foreground. And so this was our cheap test to see if we could detect the infrared. So moving right along here to the Japan earthquake, there's good news and bad news. The bad news is that I had been traveling, and I only got back to the observatory the day before the Japan earthquake, so I missed collecting all of the data that would have been, classic data, unfortunately, prior to this earthquake. The good news is I actually had been negotiating for more than a month with people at a different location to set up another camera there, and the night before the earthquake, I did set up for the first time a second camera. And so we have one at Rodeo Rd and one at Golden Eagle Observatory. And you can see in the last hours prior to the earthquake at Japan, you can see these color shifts are ongoing at both locations. We also got something that I won't go into very much here, but we call them microlights, the little tiny flashes. These were occurring at the Rodeo Rd site. 3 hours before the earthquake, the infrared sensor was flashing like mad. You can see here that in 7 of these 9 frames, the infrared sensor was illuminated. And this was pretty much consistent for the whole night. I think there were 78 flashes in that time interval. There was also the rose-colored glow at Golden Eagle. And here is an example of a color shift, and here you see a sort of a grayish, and then you see the detector detect a flash, and you can see the chromatic shift to a more pink-purple color. Okay, I'm going to skip ahead here. These are just colors before the earthquake, another microflash. This is the nearby Clarkdale. You can see purple again, and the variety of colors, and I'll skip through these. The same thing. I was taking E-field measurements. The E-field doubled right after this Clark Field earthquake. And I'll skip over that. You can see the colors. Okay, the mechanisms. Sometimes there's a capacitor-like discharge of the infrared flashers. But how do we get from trans-Pacific transmissions? There are some candidates, the Aurora, Airglow, total electron content variations. There's been corroboration by a recently published paper by Ozanov on the Japan earthquake, who he has taken infrared measurements and found them that correspond very much to our time sequence. Here's the possible capacitor. Here's a map of the total electron content. You can see that the subsolar area is massive, massively large. So reflections or some kind of skipping phenomena might be possible due to the electron content here. And this is just a hypothesis. This is what it looks like normally. This is what it looked like before the Japan earthquake. I've shifted. Japan is over here and the Pacific Basin is there. So this is one potential area. Another is called airglow, which occurs at the boundaries of the ionosphere. Oxygen species can color the airglow both into the ultraviolet. Monatomic oxygen can be red, and hydroxyl ion can give a red glow. Is there something special about Sedona? Well, before the Chilean earthquake, there was a purple fog reported in Hungary. So these are probably not just local. The aurora, we might look to that. There were many purple aurora that occurred before some of these large magnitude earthquakes. So the Ozanov data shows that he found 8 days prior to Japan, he got increases in total electron content and also infrared satellite imaging. 8 days prior, his maximum anomalous day was 3 to 4 days prior to, which corresponds to our observations. So there's something about the timing sequence here. We propose to look more closely at the total electron content, and for an area to start to investigating, we might look at radar anomalies and all of the reflection problems that they have, such as surface ducting and anomalous propagation. We might find that there are some IR and EM reflectivity. What we see is that sky chromatic shifts can be detected remotely 7 to 8 days in advance of large earthquakes. Digital cameras can detect non-optical colors. The white balance of the camera might play a part. Infrared might be a component of the chromatic changes. Anomalous infrared emissions and ionospheric changes before large earthquake have been described by Ozanov et al. At similar time intervals to what we observe. Inexpensive motion detectors are able to detect these IR flashes. UV is a possible optical wavelength that may contribute. We haven't investigated that. The mechanism for IR and UV over great distances, we look to possibly radar science, and to forecast earthquakes, let's look at the atmosphere and not the ground. Thank you.
You said you had a second camera. Was it oriented in the same direction?
Generally, yes.
Have you thought of setting up a system of maybe 3 cameras, or possibly, if you can afford it, 4, say, to north, south, east, and west, and see if there's any effect in the color and the intensity of the light compared to where the relative location of the earthquakes?
Yes, we'd love to do that. The cameras that are capable of getting high quality color cost about $2,500 or $600. So we are limited by the financial resources of how many cameras. We do have 2 cameras, possibly a 3rd camera, but they're not as good as the primary camera, which is a D700. And we would love to get the funding to do exactly what you recommended. These cameras, by the way, were facing in the opposite direction of the Pacific Basin. They were facing northeast. So whatever these changes are, they appear to be all over the entire horizon and globe.
Yeah, hi Marsha. One question everything was pretty much taken from Sedona, other than what you noted. And why aren't you using the vastly available satellite data? Because we are measuring in every wavelength possible. And it seems that, maybe even, writing a grant to try to do some modeling and working with climatologists and because there's a tremendous amount of satellite data that we are collecting on this very thing.
Well, that's great. I do review a lot of satellite data, but I'd like to talk to you and find out the availability of what is available. Yes, definitely. Thank you.
Okay, is this data hand analyzed and looked at, or is there a computer model for automating the analysis? And have you had any false positives?
Right now, it has been all hand analyzed. This is, really a prototype, initial observation, empirical data, and I am looking into being able to get quantitative and qualitative data in order to analyze it, because there were, since we've been looking at the infrared flashes, there are about 180,000 pictures and more than 1 million pictures to look at, high-resolution pictures, since we've started taking these. So I'm desperately looking to computerize. Thank you. If you have any suggestions, I'd like to hear them.
Many of the phenomena you described are similar to what HAARP is supposedly doing to the ionosphere, heating the ionosphere, which would affect the infrared. Have you correlated any of this with the activity of the HAARP station? There are some groups that track when it's on, when it's off, et cetera.
No, I haven't, and I wasn't aware that there was, I know that HAARP takes a lot of data, observational, but I'm not aware of the websites that tell when it's transmitting. I guess I'd like to know that, but no, I haven't done anything like that.
Sedona is noted for anomalous activities, I believe. I wonder if any other of the remote sites that you mentioned are also noted for anomalies. And also, do you have access to any magnetometer data?
At the observatory, we run magnetometers 24/7. We have 2 magnetometers, very sensitive down to 1 gamma. And I have not yet had the opportunity, the time to try and correlate it with these flashes. So, and as far as anomaly, that's why we.
I didn't do it. Yeah, that's right. We're going to have 2 quick questions, and then that's a wrap on this. Yeah.
Marsha, a few months ago I was at the New York Metropolitan Museum, and they had a screen up there that shows earthquakes happening around the world over the last month, and there were probably 50 or 60 of them shown, including some magnitude 6. And I'm just wondering, how are you considering that you are separating out the actual earthquakes that you're looking at versus the earthquakes that are occurring all over the world?
Hello? Okay. It's a rare day that there is not a magnitude 5 earthquake somewhere on the planet, and a magnitude 6 earthquake happens about every 3 days somewhere. So we really have to be very careful with the magnitude selection, and that's why I showed you by not selecting earthquakes using the 3 largest that have happened since the system has been in operation, and then also the largest and closest, and also the most anomalous close earthquake. They do other earthquakes do cause some noise in the system, and this is where we need to do some statistical Monte Carlo or superposed epic analysis, and this is the next step. But basically, I would say that we see the anomalies in magnitude 7 and above earthquakes unless they're almost right under our feet.
Last question.
Thank you for that talk. You're probably aware that the silicon sensors that are used in digital cameras have a basic response from 380 nanometers out to 1100, and the eye is at 555. So the sensor itself, and they put filters in front so to get the human eye response, which if you want to look in the infrared, it's just what you don't want. So I wondered if you had thought about talking to a manufacturer to take off that filter that they put on the front of the sensor. Then you'd automatically have a very wide-ranging infrared response.
Yes, that's a very good idea, and I have done that. The graph that you that you saw shows the series of filters that are in place in most cameras, and also the hot mirror, which takes out the wings of the spectrum. And I think it's Sony, it might be Sony, or there is a manufacturer that makes a camera without the hot mirror. Again, it's very expensive, and we're limited by our funding capacity. But yes, in fact, I've been salivating over getting one of those cameras.
Thank you, Marsha.